how have you calculated energy of resonance?
This state, I mean that this is just the bound state calculation.
Bound state?
Yeah. This is the binding energy ratio that we have for the tetramers.
How it can be? I mean, they're below the lowest trimer, so they're indeed stable. So these are true bound states. So you don't consider
the higher trimers. Yeah, this is just, I mean, the calculation, I mean, that for the ground trimer.
So you are not in
of course.
In the Efimov limit, actually. Well, okay, it's clear, answer is clear, but another question, which is probably related. If we compare your results with other different calculations, can you point out value of mu4 for which your result
okay. So we can
coincide with previous?
Sure. This is the prediction which is done, I mean that with the Deltuva, I mean that he obtained 4.6 for the ground when the, I mean that
but the ground is before 0, right? We need to go up.
Yeah, here, for example, yeah. This is, I mean that this can be corresponding to Deltuva. Of course, they have comparison with other groups. Yeah, the first, yeah.
Are these all S-wave or?
S-wave, yeah.
Did you see any higher part wave?
This is just a study that we did for this wave. Yeah. Okay.
You didn't check the channel with the
No. So in the next table, I have the result for the, I mean the tetramer ground and excited state binding energy for positive scattering lengths when, I mean that the first table for exactly unitar limit. So the question is that how is the behavior of the result when we approach to this, I mean that unitar limit from positive scattering lengths, and also it can be done from negative scattering lengths. So we see that here the binding energy ratios is decreasing, and for the virtual side or negative scattering length, this binding energy ratio increase. So we can see all of this result, I mean that for tetramer binding energy as a function of the ground trimer binding energy, for ground tetramer first excited and second exactly at the unitar limit in the left panel, and in the right panel we can see the trimer binding energy ratios as a dimer binding energy or as a function of the scattering length for positive scattering length. So we have the ground trimer first excited and second excited. Again, this result are for, I mean that for tetramer are given exactly at the unitar limit. I mean that B2 is equal to 0.
This is by varying this mu fold.
Yes, yeah. So, yeah.
In terms of interpreting this state that you've labeled by n is equal to 1
Yeah.
and n is equal to 2,
Yeah.
would you claim any universality that's associated with it?
Yeah, we can see this, I mean that this, okay, I mean that I forgot to say that this line is atom trimer line and this line is atom dimer line. And we see that, I mean that this, when this state appears and I decrease the trimer binding energy in this point, this, I mean that the first excited trimer appears. We can see the same energy ratio would, I mean that is about 4.6. The next, I mean the tetramer appears. So it means that they have the universal behavior that we show in our scaling plots. So we can see here, this is the, I mean the usual FMO plot that we have, of course, for absolute value of the three-body binding energy as a function of the inverse of the scattering length. This is the atom dimer line. Okay, here we have the 4-atom resonance. So we can see, for example, from a negative scattering length, a ground trimer appears. So if we increase the scattering length in this direction, we see that the next trimer appears. And again, if we increase the scattering length, we see that the next trimer appears. this condition, I mean that when the new trimer appears in this, plot can be shown, as these three angles in this scaling plot. The scaling plot is connecting two successive trimer binding energy together. Here we have B3N plus 1 minus B2 bar. B2 bar is dimer binding energy for this positive scattering length and is 0 for this negative scattering length. And here we have in the x-axis the ratio of the square root of the ratio B2 over B3N. So it means that if we have here, this is the point that in the ratio 0.03, which is corresponding to B3N over B2 visual is 1084. It means that the next trimer disappears. So it means that if the binding energy of this ratio with respect to the energy of the virtual state is reach this ratio, that next trimer appears. So it is also true for this state, and this state. So when we increase the scattering length to infinite scattering length, so we should see the Efimov trimer with the binding energy ratio about 550. So let me to start from the right direction to obtain this Efimov state. So here we have a ground trimer at atom dimer resonance. So we increase the scattering length. So we see that the next trimer appears. That this is the result that we have obtained by zero range interaction and by using this three-body regularization parameter. So when the ratio of this energy, that B3 over B2 is 6.61, then next trimer appears. So if we continue again the increase the scattering length, so we see that the next or second excited trimer appears. So it means that when the binding energy ratio of this trimer, that fast excited with respect to dimer is 6.61 corresponding to here. The next trimer appears. So this is corresponding to this energy ratio. That when the ground state energy with respect to the dimer energy is 1385. So when we approach this, all of these points are shown, that in our scaling plot in this point, because here as you see B3N plus 1 is equal to B2. So it means that the Y is equal to 0. It means that the new state is appearing, and this is corresponding to the point when the B2 over B3 and square root is 0.38. When we increase, that the scattering length and infinite scattering length, so we can see this Efimov state, and our calculations show that this point, this is corresponding to this circle that we have here. 0.044 for this ratio